So in this question here, we want to find out, does this sequence here, a of n, which is 5 to the n over n factorial, converge or diverge by the monotone convergence theorem? Now, the monotone convergence theorem, one of the rules for that is a sequence must be consistently increasing or decreasing. So if it does both, then maybe we can't have it. So let's have a look and see what we can do with this sequence here. So an equals 5 to the n over n factorial. So therefore, let's have a look what an plus 1 does. So an plus 1, that's 5 to the n plus 1 over n plus 1 factorial. So that's what the next term in the sequence does. So let's just do some algebra on this and see what we get to. So then this equals 5 to the n times 5, and then n plus 1 factorial is just simply n plus 1 times n factorial. So that's our an plus 1. Now if you have a look at that very closely, we can see an is embedded in that. We've got 5 to the n over n factorial, which is these two parts of our term. So we can rewrite this as 5 to the n over n factorial times 5 over n plus 1. Okay, and again, if this is what we've got here, this is then an times 5 over n plus 1. So that's our an plus 1. Okay, now is this strictly increasing or strictly decreasing? That's what we want to know. Well, 5 to the n over n factorial, I don't really know a lot about that at the moment, but 5 over n plus 1, we can have a look at that. So 5 divided by n plus 1. Now if we're going to multiply that by any number, 5 to the n plus 1, if it's greater than 1, then this will increase. If it's less than 1, then this whole thing here will decrease. So if we've got n equals 4, this here becomes 5 over 4 plus 1, which equals just 1. So therefore that would just be multiplying by 1 at n equals 4. So for n is less than 4, so let's put n is less than 4, that will be 5 over, let's say for example 3 plus 1. In which case this here would be greater than 1 and then would increase our an plus 1 to sequence. Now if n is greater than 4, then we'd have 5 over, for example, 5 plus 1, in which case this would be less than 1. So what we conclude is that if n is 4 or more, this sequence is consistently decreasing. So and if n is 5 or more, then this sequence is strictly decreasing. So that's the first thing we can come to a conclusion to. So if n is greater than or equal to 4, an plus 1 is decreasing. And that will be for all of those terms from 4 all the way to infinity. So that gives us some hope that we can find a way that this sequence here can converge. Now if n is greater than 4, so i.e. 5 or more, an plus 1 is strictly decreasing. In other words, every term in it is decreasing. If it's an plus 1 is decreasing here for n is greater than or equal to 4, at this term here, we're only multiplying it by 1. When n is 4, we're only multiplying by 1, in which case it stays the same. Okay, so that's what we could conclude so far on the decreasing and increasing. So now let's just have a look to see if we can find a limit and find what it converges to. And if that's the case, then we can say it converges by our monotone convergence theorem. So let's have a look at that next. So let's take this off the board. Okay, now let's find the limit of this and see if there's anything we can do. So the limit as n approaches infinity of 5 to the n over n factorial times 5 over n plus 1. Okay, now we could plug in some numbers here and see what would happen, but I'm going to split this limit apart. So the limit as n approaches infinity, I'm going to split it into two limits. So now I've got the limit as n approaches infinity of 5 to the n over n factorial. And then what I'm going to do is I'm going to multiply that by my limit as n approaches infinity of 5 over n plus 1. Okay, well, let's just break this one down here first. So the limit as n approaches infinity, this term, well, n factorial is the most powerful term. So let's divide all the terms by n factorial. So now I've got 5 to the n over n factorial divided by n factorial over n factorial. And then I'm going to multiply that by this limit, n approaching infinity. Now, as n approaches infinity here, the powerful one in this is just n. So I've got 5 over n divided by n over n plus 1 over n. Okay, well, 5 over n divided by n factorial. So 5 over n divided by n factorial. This one approaches 0 as n approaches infinity. So that's what we're going to do here with all these terms. So this term here would then become 0. Well, n factorial divided by n factorial, that's just going to be 1. So that's what we got here. So these are 0 and 1. What about this? So 5 over n. So as n approaches infinity, this is going to approach 0. So this term here will become 0. N over n will just become 1. And then 1 over n, same as 5 over n, 1 over n approaches 0 as n approaches infinity. So this one is just basically 5 times 1 over n. That's what we got there. So these are the same. So this one here, that's 0. Okay, so now we can multiply our two limits together and find our complete limit for our an plus 1. So now we've got 0 over 1 multiplied by 0 over 1. So this equals 0. So therefore, we can say that our an approaches 0 as n approaches infinity. So by the monotone convergence theorem, our a of n plus 1, or our an for n greater than 3 is decreasing and approaching 0. So by the monotone convergence theorem, this series here converges to 0 and is strictly decreasing for n greater than 3. So therefore this sequence here converges to 0. Okay.